Draw an angle in standard position, label the vertex, initial side, and terminal side. Okay, so standard position is on the coordinate axis, and the initial side will always be start with the vertex of the angle at the origin, and one side is on the positive x-axis, and then whichever direction you go, counterclockwise or clockwise, you draw the other angle, whatever the other ray, whatever angle measure it is, and that's called the terminal side. Now we commonly use Greek letters for angle labels like theta, phi, alpha, beta, gamma, so you're going to have to get used to that. Explain why there are an infinite number of angles that are coterminal to a certain angle. Well, every angle has a terminal side, but we could add on to it a number of rotations, either positively clockwise, counterclockwise, or negatively clockwise. So you can be in that same spot, and that's called coterminal if you rotate it a bunch of times. And since you could rotate it infinitely times, there could be infinite in both directions. State what positive, negative angle signifies and explain how to draw each. Well, in standard position, positive angles, you rotate the terminal side in a counterclockwise direction. That's called positive orientation, and the negative orientation is in clockwise direction. So that's what we mean by a negative angle, is that's the direction that it's the clockwise direction. How does radian measure of an angle compared to the degree measure? Include an explanation of 1 radian in your paragraph. Okay, the degree measure comes from there being 360 degrees in a circle. Now that comes historically from the Babylonians, who at one time thought that the sun revolved around the earth in 360 days, and so they divided one day was essentially 1 degree. That's where that comes from historically. So a radian, though, that occurs when the radius is equal to the arc length in which the angle has moved through. So when this radius and this arc length are equal to each other, that's 1 radian. So since we know that the circumference of a circle is 2 pi r, and if the radius is 1, that means the circumference is just 2 pi, which is how much it would go through to go all the way around. We know that was 360 degrees. So you know that 2 pi radians is equal to 360. Divide these out so you get pi is equal to 180. And you can see that's the conversions that we're using above when we create how to turn radians into degrees and degrees into radians. We just use these numbers here. Now the way I remember it is, this is the way I taught myself how to do it, is that when I want to have radians, a lot of times, that's like 2 pi and pi over 2. So there's always a pi there. So I'm putting the pi in so it's in the numerator. Now I want to get rid of the pi for the degrees, so I divide it out. And that's how I remember which direction goes which direction. Okay, so another thing that we got to get a handle on is radian measures and the unit circle. These are special angles that are used frequently, and so it helps to actually know how this picture is created. It's really created with two types of circles with the divisions. One where you're measuring in 30 degrees, right? Pi over 6 is 30 degrees. So if you go 30, 60, 90, 120, 180, or 150, 180, 210, 240, 270, 300, 330, and then 360, you're marching it all the way around like that. But if you do it in radians, and and you count in the radian measure, pi over 6, which is 30 degrees, this is 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi, 5 pi over 6, 7 pi over 6, 8 pi over 6, 9, so on as you go around. And really you just have to count by sixths, right? 1 6, 2 6, 3 6, 4 6. But some of these simplify, and that's how we get like the pi over 3 over here, is that if you simplify that fraction 2 6, you get pi over 3. And so really this is marching this thing around by 30 degrees or pi over 6, and so are these. It's just that these are simplified. Even this one, right, 3 pi over 6, 3 goes into 6 2 times, that's where we get our pi over 2. Now the other circle that's kind of built into this is the fourths, or 45 degrees. So we divide the circle into really 8 parts, right? So 1, 2, 3, 4, 5, 6, 7, 8. But if we went by degrees, 45, 90, 135, 180, 215, 270, 315, and 360, right, as you go around. But if I go by fourths, again, just like above, I go 1 4th, 2 4th, 3 4th, 4 4th, 5 4th, 6 4th, 7 4th, and back to 8 fourths. And so I can count these. And again, some of these simplify. In fact, all the ones where they're even simplify. Pi over 2 pi over 4 is pi over 2, and 4 pi over 4 is pi, like that. And so you can see that they're on top of each other. Now, these are angles we're going to use all the time, and so that's why we want to be very familiar with the unit circle. Explain the difference between linear speed and angular speed when describing motion along a circular path. Well, to really do that, you first have to understand how you find length of the arc. So the length of the arc is, this is from the book, they give you the formula, but how it's created is there's a certain fraction of the distance that you go around, right? So this is from here to here. If you went all the way around, it would be 2 pi. So this is just a fraction of it. So you take that theta divided by 2 pi, that's the fraction, divide out the 2 pi's and get r theta. That's how this comes into play. Now linear speed would be if something is on the edge, on this orange part, how fast is it moving? Well, it's the distance divided by the time. That's linear speed. The angular speed would be how much you're moving, how much this angle is changing in a certain amount of time. So that'd be theta divided by time. Now the relationship between them is if I take linear speed, and it's s divided by t, and I just substitute in what the formula is that we have up here, you'll notice that you can regroup it. So theta over t times r, well, theta over t is just angular, so the linear speed is equal to the radius times the angular speed. So what that means is then if you have a constant angular speed, the further you are away from it, the faster it's going to go. And anybody who's taken a telescope or a telescopic lens on a camera knows that when you zoom out, a little motion really whips across a long distance, because it's like having a long radius. Even though you're at the pivot point here, the distance that you're looking at is much further. So in the same distance, it has to go the same amount of time. So this distance is a lot slower than if it's way out here and you have to move. All right, one other thing is that they do is area of a sector. And again, you can also do create this formula. It's the fraction of the distance you go around in radians divided by 2 pi, and then notice the pi's divide out and you get the formula for area of a sector. Alright, for the following exercises, draw angles in standard position with a given measure. So let's do that. Okay, so let's do these problems. First one was 300 degrees. We want to draw in a rotation. Now this is not one complete rotation around, so this is, take 360 degrees is one rotation, subtract 300 from that, and that's 60 degrees shy, which would be right like that. That would be 60 degrees shy here. So our 300 degrees would be that far around. Alright, now if I do 10, negative 150 degrees. So negative means we go in this direction, in the clockwise direction, and so it's not quite 180, right? If I subtract it off, that's 30 degrees shy of 180, so we would get something like this, which is our negative 150 degrees. Alright, so then the last, or the number 19, not the last one, 22 pi over 3. Now this one, it goes around a few times before it stops. So what we want to do is we want to divide it by 2 pi, which is one full rotation. So that'd be 22 pi over 3 times reciprocal, right? Dividing by a number same. So that gives me 11 over 3, which is 9 plus 2 over 3 over 3. So that's 3 rotations and 2/3 of a rotation. Now 2/3 of a rotation would be 2/3 times 1 rotation is 2 pi, so that'd be 4 pi over 3. So 3 pi over 3 would be here, that would be just pi, so it's just one more pi over 3, so that gives us our, well, this is the last bit, this is the remainder, that's the 4 pi over 3, but really what we're doing is we're going 1, 2, 3, like that. And then we end up at the 4 pi over 3, so that would give us our 22 pi over 3. Now last one here, 20 negative pi over 6, that's going counterclockwise, so we'd be going this way, and pi over 6 is, it's about 30 degrees, so that'd be pi over 6. Negative pi over 6 is that direction there. Alright, for the following exercise, convert the angles in degrees and radians. So these are just going back to a previous slide, and it's just from degrees you want to just multiply by pi over 180. The way I always think of it is when I want to make it in radians, a lot of these angles have pi in it, so add in the pi or multiply in the pi and divide out the 180. That's how I kind of remember which is which. And this one is divide out the pi when you convert from radians to degrees. So again, you just multiply these together. Now you just simplify this fraction. And you get negative 2/3 pi. So the lower one, convert to radians, again, it's just the reciprocal, so I want to get rid of the pi's, so I divide them out, and then I put the 180 there, right, the pi's divide out, then 6 goes into 180, well, 6 goes into 18 3 times, so 30, and then you just multiply them together and you get 330. A bicycle with 24-inch diameter wheels is traveling 15 miles per hour. Alright, so we have a wheel, 24 inches, traveling 15 miles per hour. Find the angular speed. Well, we know that linear speed is equal to the radius times angular speed of the wheels at radians per minute. So we want this answer to be in radians per minute, and that it also asks for how many revolutions per minute, or right, rotations do the wheels make. Okay, so the one thing we'll want to do is we'll want to get this into this is in inches, so we want this probably in inches per the speed. We want this in inches per minute. So the one thing we do know is that 1 mile is equal to 5,280 feet. We know that 1 foot is equal to 12 inches, right? And so we could convert that. Now I want to get rid of the miles and put in feet 5280 over 1. And then I want to get rid of the feet and put in inches. So that's 12 divided by 1. So notice now that the miles divide out, the feet divide out, and we're left with inches. Alright, so then the last one is we want to convert this into minutes. So we want minutes here and hours there. So for every 1 hour there's 60. So notice that the hours divide out. So we are left with 15 times 5280 times 12 divided by 60 times 5280 times 12 divided by 60. So that gives us 15,840 inches per minute. Now what they want is the angular velocity, but this is the v. That's what that is. So we get 15,840 is equal to 24 times omega. So now I just divide the 24. So this gives me 15,840 divided by 24. This would be radians per minute. 1580 15,840 divided by 24. 660. This gives us an omega of 660 radians per minute. Now if I wanted to write this in revolutions or rotations, what I know then is that for every one rotation or one revolution, I have 2 pi radians. So that means my omega would be, so I just have to divide 660. And I get that it makes 1,300 or 1,036.7, say, rotations per minute. A bicycle has a wheel that is 28 inches in diameter. So this is 28 inches. A tachometer determines the wheels are rotating at 180 revolutions per minute. Find the speed of the bicycle. Alright, so our angular velocity is 180 revolutions per minute. Now what we want to do is we want to turn it into radians per minute. So I'd put the radians here, which is 2 pi over one revolution. So these would divide out and I would get 360 pi radians per minute. Now I know that the linear velocity is radius times omega, so the radius would be half of this, of course, which is 14. So we get 14 times 360 pi, and this would be in inches per minute. 14 times 360 pi. Alright, so that gives me 1,583.6269 inches per minute. Now if I want to convert that into miles per hour, so I have inches per minute. What I want to do is I want to get rid of the inches, so let's put feet in there. So for every 1 foot there's 12 inches. And then let's put the miles in there. So for every 1 mile there's 5,280 feet. And now we want to turn this into hours. I want hours here and minutes there. So this would be 60 minutes, there's 1. So we can take this number, multiply it by 60, and divide it by that. Yeah. Take the answer times 60 divided by 12 times 5280 and we get 14.9. Alright, since we got 14.9939, let's just round, and because we rounded off the pi part, let's just say that it's probably 15 miles per hour. Find the distance along an arc on the surface of the Earth that subtends a central angle of 5 minutes. So we have some angle here that is 5 minutes. And 5 minutes is equal to 1/60th of a degree. And 1/60th of a degree is pi over 180, which would be pi over 10,800 radians. And the arc length then would be S is the radius. Now the radius they give us in the problem for the Earth is 3,960, so this would be 3,960 times pi over 10,800, which is approximately 1.15 miles. A sector of a circle has the central angle of 30 degrees. And a radius of 20 centimeters. What is the area of the sector? So the area is theta divided by 2r squared. So now this has to be in radians, so multiply this by pi over 180. This would be pi over 6. So I have pi over 6 divided by 2 times 20 squared. This would be pi over 12 times 400 squared, or times 400. Let's see, 4 goes into both of those. So you get 100 pi over 3 for the area of your sector. And centimeter, the units would be centimeters squared because it now is area.